It happened in August 2021. China announced the completion of an experimental nuclear reactor. It was built in the middle of the Gobi Desert in the north of the country, and now it'll be tested for several years. If everything goes according to plan and the experiment succeeds, Beijing intends to create another reactor, one that could potentially produce enough electricity for more than 100,000 homes. You might think, what's so special about that? Nuclear reactors are built, well, not every day, but quite often. Nothing to make a news story out of. But there is news, and it's about the material that'll power this reactor. I'm talking about thorium. If China succeeds with these reactors, the world's nuclear energy will be transformed for good. Because, all right, maybe I should start from the very beginning. With coffee. Just an unobtrusive reminder to do something under the video if you happen to forget. So, what exactly is thorium? It's a chemical element with the atomic number 90, found in nature, a somewhat radioactive metal that was discovered in 1828 by Swedish chemist Jöns Jacob Berzelius. This metal was named after Thor, the Scandinavian god of thunder. Thorium is found in small amounts in most rocks and soils, and small amounts means about 3 times more than uranium. Keep that in mind. In its pure form, thorium is a shiny silver-white metal that maintains its gloss for several months. However, if it's contaminated with oxide, thorium slowly dulls in the air, turning gray and eventually black. And although thorium has been known for almost 200 years, historically it found little use in industry or power generation. Thorium just existed. Until China started to really look into it. In 2021, when China announced that it had completed the construction of its first molten sand thorium nuclear reactor, many newspapers called it a new page in the history of nuclear energy could be written. It's known that the first tests of this alternative technology were scheduled right after the reactor was turned on, which means they're already in full swing today. The first low-powered prototype, built near the northern city of Wuwei, can currently generate enough energy for about 1,000 homes. Yeah, that's not much. But it's all in line with China's goals. They weren't planning to use this reactor for large-scale use. The aim was just to start, test things out, and see how it goes. Because if everything goes well, Beijing could become an exporter of reactor technology. That's been the subject of discussions for over 40 years. The Chinese reactor could become the world's first working molten salt reactor. The last time this technology was used was in 1969. And after that, the U.S. gave up on its national laboratory in Oak Ridge, Tennessee. Since then, almost all modern reactors have used uranium and water as fuel. Classic. But what about the fuel potential of thorium? And what do molten salts have to do with it? Actually, the reason people still haven't figured out how to use thorium in industry partly has to do with the fact that thorium itself isn't nuclear fuel. Wait a minute. What do you mean it isn't? So what is all this about then? Well, it's a bit more complicated than it might seem at first glance. Thorium-232, the only naturally occurring isotope of thorium, is a fissionable material, but not a fissile one. This means that for fission, the splitting of atomic nuclei, which releases energy used to generate electricity, it needs high-energy neutrons. When thorium-232 is irradiated with them, it undergoes a series of nuclear reactions, ultimately producing uranium-233. A fissile material that can be burned as fuel in nuclear reactors in the usual way. And here probably is the right time to briefly explain how nuclear reactors actually work. For those who've never thought about how they operate, this will help to understand the whole idea behind the Chinese project. But if you're already familiar with it, don't worry, I'll keep it short. Nuclear reactors are basically large boilers used to heat water in order to produce huge amounts of low-carbon electricity. They come in different sizes and shapes and can run on various types of fuel. Heating happens due to the splitting of atoms, a process called fission. A neutron fires into an atom, which then splits into 2 smaller atoms and a few extra neutrons. Some of the released neutrons then hit other atoms, causing them to split too and release more neutrons. This is called a chain reaction. The splitting of atoms in a chain reaction releases a lot of energy in the form of heat. This heat is carried away from the reactor by circulating liquid, usually water, which is then used to create steam. This steam drives turbines to generate electricity, and that's the ultimate goal of a nuclear power plant. Nuclear reactors can be different. For example, some keep the water at such high pressure that even though it's at 212 degrees Fahrenheit, it doesn't turn into steam. Others, on the other hand, heat the water and produce steam directly inside the reactor vessel. But one thing remains unchanged. Water is needed in any case. And this is where the problem lies. Even the most modern and advanced nuclear power plants can't be completely safe from accidents. Accidents just happen. And in such cases, when water bursts out of the pipes under pressure, two things happen. First, the water leaks out of the system, making it impossible to cool the reactor. And second, when the water loses pressure, it almost instantly turns into gas, damaging other systems. Something like this happened during the Chernobyl disaster. At the same time, the molten salt reactor created in China works in a completely different way. With the molten salt technology, the salt itself becomes the fuel. The crystals mix with the material, uranium or thorium, are heated to over 932 degrees Fahrenheit to become liquid, and then they can carry the heat and energy produced. Here's what 2 samples of fluoride salt look like in solid form and as a molten liquid. Its boiling point is higher than that of water, about 2,552 degrees Fahrenheit, and even higher. What does this mean? Well, first of all, the pipes with high pressure can be removed from the system I just described. The liquid doesn't boil, so there's no need to make an effort to prevent it from evaporating. In theory, this means nuclear power plants become safer as the risk of accidents and explosions goes down. Besides, if there's a leak in the system, it means that it's not water leaving the system, but the fuel itself. So one of the problems is solved. The reactor won't overheat anymore due to lack of water. Another plus, the uniformity of the solution allows you to add it to the system whenever needed. You don't even have to shut it down. To give you an idea, in a system with water and uranium, replacing fuel in a reactor is a long and expensive process because it requires stopping the reactor. But here you can add fuel whenever you want and remove spent fuel whenever needed. Complete freedom of action. And that already sounds pretty cool. But thorium's ready to offer humanity much more. One more advantage of this reactor is that it doesn't need to be built near water sources. The salts themselves act as a coolant. This is different from regular uranium power plants, which require huge amounts of water to cool the reactors. Thanks to this, reactors can be placed in remote and dry regions like the Gobi Desert or any other desert. There's plenty of that in China. The benefit here isn't just that the reactor in the middle of nowhere will make use of empty land, it also means the station will be far from populated areas. And if a serious accident does happen, it will affect fewer people, and the consequences could be potentially less destructive. So it's no surprise that many countries see thorium as a viable and super appealing option for generating electricity, especially since energy demand is skyrocketing everywhere. Besides the advantages I've already mentioned, thorium can produce more fissile material than it consumes while fueling a reactor. Also, according to experts, whom I've no reason to doubt, the upper part of the Earth's crust contains an average of 10.5 parts per million of thorium, compared to about 3 parts per million of uranium. Another advantage is that thorium-fueled reactors can be much more eco-friendly than their uranium counterparts. I mean, nuclear reactors in general don't emit greenhouse gases while running, but thorium ones also produce less long-lived nuclear waste than modern uranium reactors. All of this comes in handy for humanity, which has started seriously thinking about tackling climate change. The world is actively searching for alternative, sustainable, and reliable energy technologies, and thorium has every chance of becoming one. Especially since at the 2023 UN Climate Change Conference, more than 20 countries pledged to triple global nuclear power capacity by 2050, all for the sake of cutting emissions. But it's too soon to celebrate. Well, at least we shouldn't forget that there's a major stumbling block when it comes to promoting thorium as the greenest fuel. No one has tested it on a commercial scale yet. Or is it just a matter of time? China isn't the only one looking to tap into thorium's unique properties. In the past, India, Japan, the UK, the US, and other countries have shown clear interest, at least when it comes to exploring thorium's potential for nuclear energy. For many years now, there have been news reports about Russian scientists developing technology for building low-power, high-temperature reactors that run on thorium fuel. But so far, it hasn't gone beyond news and talk. And judging by examples from other countries, it might stay that way for a long time. In India, talks about using thorium have been going on since the 50s. And that's no surprise, as scientists are looking to secure the country's long-term energy independence by tapping into its uranium and thorium reserves found in monazite, i.e. radioactive sands, along the coastal areas of South India. Thorium's especially appealing to India because the country has only about 1 to 2% of the world's uranium reserves, but holds one of the largest shares of global thorium reserves, around 25%. That's why they pay a lot of attention to this element. In fact, India has published about twice as many papers on thorium as its closest competitors during each period from 2002 to 2006. And according to estimates from India's atomic agency, the country could generate 500 gigawatts for at least 4 centuries using just its economically extractable thorium reserves. It just needs to get to work on it and, of course, mine the thorium. Like I said, the most common source of thorium is the rare earth phosphate mineral monazite, or monazite sand, which contains up to 12% thorium phosphate, but on average about 6 to 7%. Monazite, on the other hand, is found in igneous and other rocks, but the highest concentrations are in placer deposits. These are clusters of small rock fragments. There are about 16 million tons of monazite in the world, with 12 million tons located in heavy mineral sand deposits along the southern and eastern coasts of India. Makes sense, that's where thorium is found too. As for thorium, there are significant deposits in several other countries: Brazil, Australia, the US, Egypt, and India is in first place. China, however, doesn't even make the top 10, ranking 11th. Its thorium reserves are more than 8 times smaller than India's, but even this relatively small amount's actually quite significant. By the way, thorium's already being mined in India, Brazil, Vietnam, and Malaysia. But the production volume's probably less than 10,000 tons per year. Unfortunately, without the commercial extraction of rare earth elements, thorium production is not profitable at the moment. For now. China clearly has a role to play in the future because thorium belongs to a well-known family of rare earth metals, which are much more commonly found in China than anywhere else. When it comes to rare earth metals in general, China's the leader in the market. These minerals are key components in everything from wind turbines to electronics, and China's responsible for 97% of global supplies. With all this in mind, thorium, which naturally accompanies rare earth metals, is like the cherry on top for the Chinese authorities. By using it, they can enhance their energy independence from big uranium exporting countries such as Canada and Australia. And let's just say the diplomatic ties between China and those countries can sometimes be a little shaky. Investing in thorium is a long game. Right now, the country has enough uranium to fuel all the reactors in operation, but if the number of reactors increases, there could be a shortage, and using thorium could sharply reduce the need for uranium. This makes it a potentially more sustainable option, especially since thorium is readily available. No need to import it. And here you, like me, may already have a question. If thorium's so great, why has it only been considered for use now? I mean, it's been almost 200 years since its discovery, and I found the answer to this question. People considered uranium-235 as the only candidate for nuclear reactors. Did it work? It did. No one really thought about alternatives. Besides, to be honest, thorium as a fuel is still more complicated than uranium, since it requires using a breeder reactor, and global uranium prices are still pretty low, so why go through the extra effort? There are also a number of economic and technical barriers that make it difficult to use thorium, mainly, of course, the price. Yes, thorium is quite common, but it's expensive to mine. Without the current demand for rare earth elements, monazite wouldn't be mined just for its thorium content, because thorium is simply a byproduct and extracting it's much harder than uranium. And where there are difficulties, there's also high cost. However, all this could change if the demand for thorium increases, that is, if its use in nuclear energy grows. It's true that research, development, and testing of nuclear reactors are expensive, basically everything that needs to be done before we can start running thorium reactors on an industrial scale. The cost is due to the lack of significant experience. We know a lot about uranium because that's what we've been working with. While thorium, it's just there. One more issue with thorium is that it's hard to work with, being non-fissile. It requires uranium or plutonium to start and keep a chain reaction going. Molten salt reactors also raise doubts among many experts. This is because their creation brings about additional technical problems. At extremely high temperatures, salt can eat away at the reactor structures, which need to be somehow protected. How? Nobody knows yet. According to experts, even if China ultimately wins, it shouldn't get too excited. Yes, it's about the corrosiveness of the salts. The damage will only become clear in 5 to 10 years. Moreover, there's an opinion that the reactor, which generates not only energy but also uranium-233, is just a bad reactor. Because uranium-233 is an isotope that doesn't exist in nature and can be used to make an atomic bomb. There's absolutely nothing good about atomic bombs. However, the stakes for the Chinese tests are clearly high, and they'll be closely watched all over the world. Because if it works out, it could really change nuclear energy forever. It's clear that China isn't too keen on sharing details about its plans, but it's known that the country plans to build the world's first nuclear power plant with molten salt reactors in the Gobi Desert. Construction of the reactor will start in 2025, and its technical specifications include a graphite core 10 feet tall and 7 feet wide, a working temperature of 1,292 degrees Fahrenheit, thermal power of 60 megawatts, and an experimental supercritical carbon dioxide-based gas turbine in a closed loop to convert thermal power into electricity. They aim to finish the reactor by 2029. It may seem like some kind of unreal plan, way too ambitious, but it looks like China's used to it. Look, here's a simple example. In 2024, the world produced about 70 billion solar panels, with the overwhelming majority coming from China. It's hard to deny that solar energy today is revolutionary, and partly that's because of how fast it's growing. In 2004, it took the world a whole year to install 1 gigawatt of solar power. In 2010, it took a month. In 2016, a week. By 2023, there were individual days when 1 gigawatt was installed worldwide, and in 2024, 520 to 655 gigawatts were installed. That means in one day, we got as much energy as 2 full years of 2004. Such extraordinary growth is the result of the interaction of 3 simple factors. The first, when industries produce more of something, they do it cheaper. The second, when things get cheaper, the demand for them grows. The third, when demand grows, more of the product is produced. And yep, the circle's complete. In recent years, Chinese manufacturers have come to dominate the global production of solar panels and their components. Over the past decade, the price of solar panels has dropped by about 75%. Polysilicon is the main material for solar panels. Its production and processing from raw materials require a lot of energy, and Chinese manufacturing companies use coal, the dirtiest fossil fuel, as the energy source for their polysilicon plants. Since coal is cheap, it also lowers the cost of solar panels made in China. If cleaner energy were used in production, solar panels would be more expensive. Of course, this is a whole separate topic for discussion, or even a full video. Experts and even ordinary people argue a lot about how good cheap solar panels really are, given that the methods used to make them are questionable. But one thing's for sure, the solar panel boom in China is making solar energy more available worldwide. This really shows the kind of impact China and its energy industry can have on the world. Maybe thorium's destined for the same fate as solar panels. Only time will tell. The biggest news in the last few days is that I've recovered. Well, almost. Europe joins the game. Not only China understands that developing a thorium nuclear reactor could change the world. For example, the Danish molten salt reactor developer Copenhagen Atomics and Paul Scherrer Institute in Switzerland have signed a large-scale experimental collaboration agreement for 4 years. As you might have guessed, they're also planning to work with thorium, but they're still in the experimental stage. So what exactly are they planning to do? Well, first they want to test the thorium molten salt reactor technology and also share their experience with other specialists for further collaboration. If everything goes well, the data they gather will be used to model a thorium reactor for commercial purposes. Actually, Copenhagen Atomics has been developing this technology for almost 10 years. And now the time for serious experiments has come. The company's already producing and testing full-scale prototypes of test reactors at its headquarters in Copenhagen using lithium, thorium, and low-enriched uranium fluoride salt as fuel. Obviously, Copenhagen Atomics isn't working purely out of enthusiasm. The company has commercial projects. For example, it's implementing a high-purity salt technology for concentrated high-temperature solar energy, as well as energy storage using molten salt. To give you an idea of how serious the company is about its work, in 2022, it raised $21.2 million to speed up the development of its thorium reactor technology. So a thorium reactor from Europe might be here pretty soon. The Netherlands development. Thorizon, a Dutch company, isn't falling behind either. It's raised almost $13 million to develop a new generation of nuclear power plants. What's the deal with them? It's all really interesting. The Dutch have developed an advanced nuclear technology that's safe and can use existing nuclear waste as an energy source. You know, this is a big problem right now, and the company Thorizon is going to solve it for the good of society. Why can this technology be considered safe? The thing is, it uses a different type of fuel and coolant compared to traditional nuclear reactors. It's based on molten salt instead of solid fuel and water. What about efficiency? The reactor called Thorizon 1 will provide 250 megawatts of industrial heat. It can be used directly in industrial processes like in the chemical industry or for hydrogen production. Plus, this amount of electricity will be enough to meet the needs of 250,000 households. And the company can turn 100 megawatts into 50 to 300 megawatts of flexible power, storing energy when demand is low and releasing it during peak hours. The investment received will be really useful for the company's testing and research, since Thorizon has a grand goal to implement the first reactor system of a new type by 2030. Toxic mining. As I mentioned before, China's responsible for 97% of the world's supply of rare earth elements. They're needed for just about everything, from smartphones to GPS receivers, and also for wind turbines and, of course, electric vehicles. 2/3 of all rare earth metals are mined in Bautu, Inner Mongolia. However, the concentration of rare earth elements in the ore is very low. So to extract them, the ore needs to be processed using hydrometallurgical methods and acid baths. All of this leads to the creation of massive amounts of waste, which is a problem for the local population. The waste is stored in a kind of lake that holds all sorts of toxic chemicals, as well as radioactive elements like thorium. When they get into the body, they cause pancreatic and lung cancer, as well as leukemia. This fact alone sounds very sad, but it's also important to know that there used to be a huge field where the toxic lake is now. Then factories were built. Minerals started being mined, and now we're here. Industrial waste replaced watermelons and tomatoes. Rare earth elements started being mined in this area back in 1958, and by the end of the 1980s, the first negative changes began to show. Yields in nearby villages started to drop. Sometimes there was no harvest at all, and sometimes the fruits were tiny or smelled awful. As a result, many farmers abandoned their fields and stopped planting anything except wheat and corn. According to a study by the Municipal Environmental Agency, the problems were caused not just by rare earth minerals, but also by dozens of new factories that sprang up around the processing plants. On top of that, there was a fossil fuel power station that supplied energy to the new industrial setup in Bautu. All of this couldn't lead to anything good, and in addition to withered fields, the soil and groundwater also became contaminated with toxins, and farmers had to get rid of their sick livestock. What happened next? Well, the farmers left. Those who stayed tried selling the waste from the pond, which still had high levels of rare earth elements. People had nothing else left, since farming had faded away. Long story short, you get the idea. Minerals are great, but waste disposal is a must. You owe me a like. See you later.